are now recording. Okay. So a couple topics today. First one out of 9.5, the homework will be section 9.5. And we're going to be interested in two things: volume and surface area. So, and our main goal would be to look at formulas associated with volume, and then also surface area. So we're talking about space figures. General term, 3 dimensions. All right, so surface area, we're looking at the different what we'll call faces of this thing, figuring up the surface area of each face and then adding it all up, and that would be our total surface area. Volume is looking at the space within a certain figure, and how many 1 by 1 by 1 cubes can we stuff inside there. Hence, volume is cubic units. Surface area will be in square units. Right. So, just as a kind of a name game, we're going to look at just a few of the types of space figures that we deal with in Euclidean geometry. And one type, I'm going to head over the title polyhedra. So again, poly, many. Not sure about hedra in terms of meaning, but basically it does mean sides, so to speak. So, but polyhedra, what makes it distinct as a type of space figure is the spaces of it are made up of polygons. So, and I'm going to list out just a few of the types of polyhedra, kind of like when we looked at polygons and we said, 3-sided polygon is a triangle, 4-sided quadrilateral, pentagon for 5-sided, so on and so forth. So it's kind of following along the same lines. But the first one we're going to look at is tetrahedron. Now, excuse me, 4 faces, and they're made up of triangles. Now, and the type that you would see most often are regular, and that term will apply in the same way it did for polygons, where for a regular polygon, it meant all the sides were the same length. Tetrahedron, all the faces are congruent. So in the case of a tetrahedron, it is made up of 4 equilateral triangles, 4 faces. And in the case of a regular, it would be equilateral triangles. Next one you will see around hexahedron, 6 faces. And if we're thinking about these all being regular again, then each face will be a square, and we more generally refer to that as a cube. Octahedron. Octahedron, 8 faces, and they're made up of equilateral triangles. Dodecahedron, 12 faces. and they're made up of pentagons. So each face is a, and if it's a regular dodecahedron, um, excuse me, 12 faces, and each one of them is an equilateral.
According to that, each of us is
Each one of them is a, again, regular pentagon. And then 20 faces, equilateral triangles again would be each face. My favorite one, isohedron. So these again are just some of the different types of polyhedra that as examples. But again, what makes it is a space figure where each face or side is made up of polygons. Anyone who's ever gotten into role-playing games with dice, like Dungeons and Dragons, that's the type of dice that you use in those games are polyhedra. So, all right. A couple other types of space figures we'll run into. Pyramid and prisms. All right, so a pyramid has, excuse me, and if you can visualize over in Giza, Egypt, the three big pyramids out there, but triangular faces with a polygon base of some sort, usually like the ones again in Egypt are square base, but they can be any kind of polygon base, but for triangular faces, making it up. A prism has congruent kind of on the ends some type of polygon. Could be a triangle, it could be a square, it could be an octagon, and then along the face from end to end. So I can't draw, but there's kind of a side view of a prism. But you could have a triangular ends here. It could be square ends, but they're polygon. And from then here to here is a parallelogram through here. Most commonly used in physics, we can shoot light through them and it refracts the light, and we can actually see the spectrum of colors that make up light that normally we don't see unless we refract through it. All right, so and then of course in a more, getting away from straight edges, we can deal with spheres and cones, toruses, basically a donut. Also, and this does show up on Praxis. I'm not going to do a lot with it, but if you hear the term nets, right, so not as in like a fishing net. A net is something like this, laid flat on a two-dimensional surface. And I'm trying to make this look equilateral, but something like this, something like this, something like this. So it's all laid flat. And the idea with a net is, and the kind of question you would see on Praxis, you'll be given something like this and asked, if I fold up these faces, what polyhedra will I form? In this case, it's a tetrahedron. You would basically, this end would flap up, this end would flap up, this end would flap up, and we would have that 4 faces of equilateral triangles if it were regular. A cube net, and wish I could draw. Okay. And again, I could fold up these two here. This one folds up, this one folds up for that fourth face here, and then this would be the lid. So, a little bit more difficult. I'll do one more. Challenge myself here. Crossed, such. And okay, so that okay, so I wish I could draw. Okay, so 1, 2, 3. I think I have them all now. And this would be the net, or my attempt of it anyway, for an octahedron. So let's see if we got them. 1, 2, 3, 4, 5, 6, 7, and 8. 8 faces all. Again, if it were a regular octahedron, it would be all equilateral triangles. All right. So not going to even attempt to draw the net for a dodecahedron, though. That's something you could easily look up. All right. So what we're going to do now is go through some more common space figures and their volume formulas and surface area formulas, and kind of make sense of them. So anytime if I flip a page and you need to see something, nothing's erased, I can always turn the page back. So I'm going to turn the page. And I'm going to look at rectangular box. So can't draw, but someone taught me years ago. You need to draw or represent a rectangular box. You make an array of dots like this, and then click connect dot like this. Then you can bring your sides together like such. And then this would be the back side. So rectangular box. So it's going to have 6 faces total, 4 around the sides, and then top and bottom. And so if I just took one face, like here, we could have a length, that's an L, and a width. But then for the depth of it, we also have, and usually represented by H, this length right here. So if length, width, and height were all the same, then we'd have a cube. So the volume is easy enough to remember, and we'll represent that with a capital V. It's length times width times the height. Now, if we are dealing with surface area, and we'll use capital S for that, and surface area will be find the area of each face and then add all that up. So in the case of if it's a rectangular box, you would have this face, length times height in this case, and then there would always also be a dual congruent face to it on the other side, opposite of it, and that would go for each of them. So in the day, I would have one would be 2 faces that would have the area of length times width, and there would be one on the back side. And then there would be 2 that would have length times height, like these 2. And then you would have this one width times height, and there would be two of those. Excuse me. Okay, so now if length, width, and height were all the same again, you'd be dealing with a cube or hexahedron. And the volume would simply be the side length, whatever that is, because they're all going to be the same, and then power 3. And your surface area, you could length, length times width, they would all be the same. And of course, you would be just the side length and squared, but there would be 6 of those, 6 faces. So 6 times the side length squared. So when you worked your homework and you're looking at quiz and test, you're going to be able to just pull the notes and have the formulas there. Just need to be able to use them. Though you want to keep in mind certain problems on praxis, formulas like this, they do expect you to know. These aren't hard to remember, but they do have that expectation you're going to know them. Okay, let's move on. I'm going to talk about what we're going to call a right. This does deal with a right angle, right circular cylinder. All right, pop can. Think of the pop can. Try to best rendition. All right, so where the term right comes from. Basically, we have top and bottom. Both ends are circles. They're congruent, or what we call, there's not really a term congruent circles, we call them concentric. They have the same radius. Your radius right here. And where the term right comes from, if I drop to the center of the bottom circle, and I visualize this setting on this base on a parallel plane. This hits down at the bottom at a right angle. Okay. So you can have, if you just have a circular cylinder, it could be that the base is at an angle of 30 degrees from the plane in which it's setting on, which means if you kind of set it down, it would just eventually tumble over. But we normally deal with right circular cylinder, but that's where the term right comes from. This segment right here is referred to as the height. And so for finding volume, remember it's cubic units. So inside here, you're simply going to multiply the area of the circular top or bottom. They're going to be the same. And that area of a circle is pi r squared times that height. And that would give you cubic units. So that one's not too bad to remember. This one looks a little more complicated, though we'll kind of talk about the parts of it. It's got basically 2 terms. Now, so surface area, we're dealing with outside here, square units, how much surface area do we have, and that includes top and bottom. So as far as from here down to here, excluding out the circular top and bottom, I would take its circumference around here. Circumference of a circle is 2 pi r. Multiply this then by the height. Now, to add in the surface area of the top and bottom, it's area of a circle, which is pi r squared. And there's two of them, top and bottom. And so that would be the surface area formula for a right circular cylinder. Next popular one. And I forgot I just reset to that again. Sphere. Forgot to put the P in there. All right, so sphere. So sphere is a spatial figure out in space. All points on the sphere are equidistant from some fixed point we call the center. And from that center out to any point here in the sphere, we have what's called its radius. So this formula, really hard to explain where this comes from without actually getting into a proof or using some calculus and integration to prove this. But it has a constant factor, 4/3. And remember, we were dealing volume, so it's cubic units. There's one input, it is the radius. So it is 4/3 pi r cubed. Surface area has a constant factor of just 4. Remember, it is squared units, so it is pi r squared. 4 pi r squared. I'm going to put one more on this page. A right circular, so kind of like cylinder, cone. All right, so right circular cone. So much like a right circular cylinder, circular base, it would have a height from the point of the cone down here, and it hits at a right angle. And we'll call that height. All right. Volume, cubic units, sort of looks like sphere. You can remember sphere, but it's not 4/3, it's 1/3. And then it is just like cylinder, pi radius squared times the height. So I always kind of remember, when I had to remember these formulas, if I could remember the volume formula for right circular cylinder, which was pi r squared times the height, if I envisioned the cone, kind of like right here, inside this cylinder, same circular base, I just wanted 1/3 of that volume. So I wiped out 2/3 of it. If I could fit this cone exactly inside here. But that is its volume for. Now, surface area looks a lot crazier. It's pi times r. Then it's times square root. And inside the square root is the sum of radius squared plus the height squared. And then remember, we're dealing with surface area. So we've got this bottom, circular bottom. And so area of the circle, pi r squared. So we tack that on, add that on. So this term right here deals with the surface area all around the cone. And then the last term is just that circular bottom. Now, in looking at this, particularly the square root, where it's coming from, if I look at this height and then the radius, and then I take this, the hypotenuse of this triangle here, that is just coming straight down outside that cone right there, and I were to say, solve for that length would be the square root of r squared plus h squared. It's referred to as the lateral height. So here's your height. Come down on this side here, again referred to as lateral height. So it's, excuse me, pi r, then times the lateral height, and that gives you your surface area all around the cone. And then again, add on the circle, area of the circle. One other, I think I can fit it right on this page here. Pyramid. All right, so remember, it's got 4 triangular faces. I'm going to attempt to draw. It's my rendition. Then inside here. Okay. Now, so again, it can have any kind of polygon base, which within these triangular faces all around here. Generally, it's a square base, but that's not set in stone. So the way, and we're only going to look at volume of this thing, we're not going to consider a surface area formula because there's so much variation. But the volume will be 1/3, so it's kind of like cone. But then we multiply, we're going to say capital B times H. Now H is still, from the top point down, hitting that base perpendicularly, and that's your height. B represents the area of whatever base is making up that pyramid. So capital B is area of that base. And so it would just depend on what kind of polygon was making up the base. And then you would be adding up surface areas of the number of corresponding triangles, depending upon that, again, base. If it was a rectangular base or a square base, and you would have four equilateral triangles to add up the areas of each. And in that case, it would be 1/2 base times height. All right. Any questions? It's pretty dry. Want to look, excuse me, one homework problem. So on the homework, there are 11 problems, 9-5. Go in. And so just look at one as an example. I'm going to flip the page. So this is from homework 9.5. And this is number 8. All right, so it's just find the volume of a road construction marker, a cone. So it is a cone. It's a cone. And this, if we're out to find the volume, first thing I was like, what was the volume? That was the 1/3 pi times r squared times the height. And it's just put in the inputs given. So for this cone, has a height of 4 feet. And base radius. So when it says base radius, that's that circular base. And it is 1/5, so it's a fraction of a foot. Now, and this is, I wish it wouldn't do this. I wish it would just allow within the, for you to use the pi button on your calculator, but it says use 3.14 as an approximation. So when it says that and you read that in the problem, just use 3.14. Don't hit the pi button. You're more than likely get frustrated. It'll be off by a 1/10 or even 100th, and it won't count the answer correct. So, but literally, it's now just plug in here. So volume would be 1/3. And there I go. I always want to use pi, and it does tell you you're going to, I think, round this to the nearest 100th. So times 3.14 pi. Radius was 1/5 all squared, and then your height was given to be 4 feet. And it's then just a matter of putting that all in your calculator. Now, I honestly do not have left my graphing calculators at school. I need to run out and get them. But when I would be multiplying it just on a regular old calculator, I would just simply go 1 divided by 3. Right, so you get 0.3 repeating, then times 3.14. Times 0.14. And then I've got 1/5 all squared. So, which would be 1/25. So on a scientific calculator, I'd just say divide by 25, 1/25. And then times 4. All right. So approximately, and I'm going to carry it out to 4 decimal places, I get 0.1675. If it asked for, I believe it was hundreds place, so I'll be rounding it to 0.17. This is a volume, so it's cubic feet. All right, I'm going to put this in, see how I did. 0.17. And then it has you select on the units, either linear feet, square feet, or cubic. And of course, this will be cubic feet. Okay. And MathLab likes it. So it's just plug into the formula for the most part. All right. Any questions? All right. So there's one more thing I want to cover, and it's circling back to the very beginning of the semester. And I was talking about a sequence. And the sequence looked like this: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. We'll go one more. 89. Okay, so the sequence generates itself. You get the next term of the sequence by adding the 2 previous consecutive terms. So 5 plus 8 is 13, 8 plus 13 is 21, 21 plus 34 is 55, etc. You can just chat it in somebody type it in. What's the name? What is the name of this sequence?
Fibonacci.
It is Fibonacci. And so when we talked about it briefly at the beginning of the semester, I said it applied itself to literally thousands of things, both in the natural physical world as well as all kinds of man-made things. A lot of paintings in antiquity. I also, I think, had their frames, rectangular frames, conform to a certain number. I think I also mentioned the front of the Greek Parthenon. This rectangular front was also conforms to this number. Now, what I'm specifically talking about is a rectangle and this special rectangle that a lot of art in antiquity conformed to was the length divided by the width to be approximately, if we round it to hundreds place, 1.62. Now, the exact value, length, and that means no decimal form. The exact value is up in the numerator 1 plus the square root of 5, all divided by 2. Which, if you do the arithmetic and round it to hundreds place, is 1.62. When the length divided by the width is around this 1.62, or exactly this, it is referred to as a golden rectangle. And this is called the golden ratio. So it gets its name. What made it, what makes it golden? Why is it the golden rectangle? It's more special than any other rectangle. It's our rectangular viewing. We're kind of ignoring periphery here, but our rectangular viewing window that we all see. And though it's small measurements, we're all a little bit different length and width, but all of us conform to this golden ratio. If we took the length and width of our viewing rectangle, it would always come out to be about 1.62. So hence art in antiquity, it was believed that since that is our viewing rectangle, anything that conforms to this ratio would be the most pleasing thing to the eye. So where we're at now is, what in the wide world of sports does this Fibonacci sequence have to do with this golden ratio and the golden rectangle? What is the connection? All right, so what is that connection? And there is a very direct connection between the two. I'll go ahead and do normally I would have you guys do the arithmetic, but I'm going to go ahead and punch the numbers up on this here. Okay. I'm going to look at ratios of consecutive terms of Fibonacci sequence. And I'm going to start with just the very first two terms, 1 over 1, which is 1. And then I'm just going to continue this for a while. So then I'm going to go 2 over 1, which is 2. And then the next one down the line would be 3 over 2, which would be 1.5. And then it would be 5 over 3. which is 1.6 repeating. 1.6 repeating forever and ever and ever. So the next one after that would be 8/5. And then in decimal form, that is exactly 1.6. And right all at this point, you can kind of see where this is headed. But we're going to do a few more. We'll go 13/8. And 13 divided by 8 is 1.625. 21 divided by 13. The next one. I'm going to carry, these are all, because I'm rounding, but I'm going to carry out a good number of decimal places. 1.61538 and we'll do one more. 34/21 will be the next one. That's going to be 1.61904,762. Now, if I take what I said was the exact value here, can't do it on one shot, so okay, so I'm going to carry it out several decimal places. I actually get 1.61803398887, and it keeps going. In fact, I think I want to do one more of these consecutive term ratios, 55/34. And 55 divided by 34. It's actually 1.61764,706. Anyway, so from here on, if I would round to hundreds place, I would be at 1.62. If I kept, now this goes on to infinity here in this sequence. If I kept going, each time if I went out to the 100th, ratio of consecutive terms of Fibonacci, what would just start happening is, I've locked in the first two decimal places for sure. If I would just go a few more, I would lock the 8 down, and then the 0, then the 3, then the 3. And I can, much patience as I would have to keep going out farther and farther and farther. They approach this number. If we would go on and study a mathematical concept called limit, we can prove that the limit, as the number of those ratios of consecutive terms of Fibonacci goes to infinity, that limit is exactly this number 1 plus square root of 5/2. And that is the connection between the two. You would just, on the outset, you would never think there was any connection whatsoever, but they're actually completely intertwined. All right, so in the last problem of the homework on the Fibonacci, and I think there's 5 of those problems total, deals with the last thing I want to show you, and that is I want to derive this number, this 1 plus square root of 5 all over 2. That exact number. And it's going to require quadratic formula. So that's going to be, I'm going to flip the page, and that'll be the last thing we do today. So I want to derive that exact value. So this is how this is done. So we assume we have a golden rectangle. Length and a width. All right. Now, when the length divided by the width is equal to length plus width all divided by length. So an alternative definition of golden rectangle, when this proportion is true, the rectangle is golden. Right, and so it's going to be through this that we're going to be able to derive that 1 plus square root of 5 over 2. Very common. You pick up a book, the golden ratio. Most books you pick up will use the Greek letter phi to represent that golden ratio. So I'm going to say let's let phi equal length over width. And we're going to use that to make a substitution to kind of simplify this. So the first thing I'm going to do with this proportion is I'm going to split this into 2 fractions. Since we're over one denominator, I could write this as length over length plus width over length. Now we're going to use this and make the substitution. This is length over width, so we're going to write in phi. That's L over L. That's just a form of 1. And notice that this is width over length, which is the reciprocal of this. I've just flipped it. So we wouldn't put phi in there. We would put 1 over phi, or the reciprocal of phi. Next thing I'm going to do is multiply every term by phi. All right, so if it's an equation, I'm allowed to do that as long as I multiply every single term by the same thing. I'll have an equivalent equation. And the goal here is to clear that fraction. Now that on this side, that's going to give me phi times phi is phi squared equals. Now it's phi times 1, so that is phi. And then here, I'm just going to be left with 1. That was the goal, was to get that phi in that denominator to cancel out. All right, so we have a highest power 2, we have a quadratic equation. So we're going to set this equal to 0, which means I'll bring these 2 terms over. So I'll be minus phi, minus 1, and then on this side, I'll have left 0. All right, so phi is the variable. And this quadratic is not factorable. No way we're going to find 2 things multiplied to be -1 and add up to be -1. So that's where we'll turn to the quadratic formula. So reviewing that real quick, for any quadratic equation, the coefficients A, B, and C, variable x, this is set equal to 0. Then solutions for x are opposite of b plus or minus square root b squared minus 4ac all over 2a. So for us, in this quadratic equation, our a is 1, our b is -1, and our c is -1. Okay. Excuse me. All right, so let's plug this all in here and see what we end up with. So opposite of b, opposite of -1, plus or minus square root b squared, or -1 squared, minus 4 times A is 1 times C is negative 1. Then all over 2A or 2 times 1. So simplifying this out. Opposite of negative 1 is 1. Plus or minus square root. Now inside here, negative 1 squared is 1. And then this will be double negation because you got negative 4 times negative 1. So it just ends up being 1 plus 4, which is 5. And then down the bottom, 2 times 1 is 2. So there are actually two answers here. There is phi is 1 plus square root of 5 all over 2. There's our golden ratio. But there's also phi equals 1 minus square root of 5 all over 2. And so again, that was the, I'll just call it GR, golden ratio. But then there's this other number, and there's a problem within the homework that is going to deal with this other number. Okay. Any questions? Okay, so on homework, go ahead.